الله الرحمن الرحيم. Before I discuss the golden output generator and the comprehensive test bench for the GCD circuit, I would like to point out a very subtle error, error that we made during the coding of the GCD, which is not related to the GCD calculation, but rather to interfacing with the Go signal. Let me show you um, the picture for the ASM chart, okay? Because the error that we made was basically logical more than syntax error or something like that. So, okay, so here, the purpose of S0 and S1, we said before, is actually to detect a positive edge. Okay, positive edge on Go. Okay, on Go. Now, the Go signal itself can from the initial state and going to S0, the Go signal can have two values here because the transition here from the initial state to S0 is unconditional. So it just takes one clock cycle. Once the circuit is up and it reset, so it wakes up on the initial state, the next clock cycle, the next edge, it will move to S0. So Go itself is really, I don't care for this transition. Okay. However, it really matters what the value of Go is, because if the value of Go is 0 here, then you are going to miss one positive edge of Go. If let's see, so if Go is 0 and you come here, Go is 0, Go is changed to 1 here. Okay. If Go is changed to 1 here, then what happens is that this one is going to stay here forever. Okay. And then once you change it to 0, once you change Go to 0, you can go. So it will actually detect the next edge rather than the first edge on Go. So the way to fix this is to add a condition on Go at the initial state. If Go is 0, then we actually go to S1, because here in S1 we are expecting Go to go from 0 to 1. Okay, so just by going from 0 to 1, this is a positive edge by itself. If Go is 1, on the other hand, then it needs to go to 0 and then go to 1. Okay, so the correct state, if Go is 1, is to go to S0. Okay, so and to fix that, I'm not going to fix the ASM chart, but rather I'm going to fix the Verilog code. Okay, I'm going to show you how to fix the Verilog code and then move on to the comprehensive test bench. Okay, there is also another state that we are coming from to S0. The same goes for S2. When X and Y are equal, okay, we should actually either go to S0 or S1 based on Go. Okay, if Go is actually 1, we go to S0. If Go is 0, we go to S1. Okay, so this is exactly what we are going to change here. It's actually the next state logic. Okay, the next state logic. Let me share my text editor and show you what is going to change here. So this is the actually GCD module. And in the initial state, this is the initial state logic here. We are just simply going to S0. Okay, S0, but this is wrong. If you remember, we have to check Go. Okay, if Go is 1, then we go to actually, if Go is 1, then we go to S0. If go is 0, then we go to S1, okay? If go is 0, then we go to S1. Why? Because basically there is only one change that needs to cause on go. There is one change that needs to go to cause a positive edge on go, okay? And that is actually S1. S1 is checking if go is 0 and changing to 1, okay? Similarly, for coming back from the equality here, okay? So if go is 1, then we go to S0. Otherwise, we go to S1. It's exactly the same logic. S0 is 1, so S0 is 1, okay? Having fixed that, okay, we now I'm going to show you now the logic for the Python code for generating the test files, okay, test files for a comprehensive test bench. Notice that I'm using Python here, but it is clearly up to you to use whatever high-level language to generate these files. If you want to generate them using Java, by all means. If you want to generate them using C, which is actually more closer to hardware, then this is even better. Okay. So basically, the high-level language for generating the test data is your choice. This file looks exactly similar, almost the same as the one for the generating the test inputs for the multiplexer, if you remember. But the only I have changed the file names here, and I'm generating also 1,000 tests. Okay, I'm just adding underscores for the names here. Okay, and I no longer need this function actually, which is basically changing to binary, because I'm going to actually use decimal even in Verilog. Okay. Okay, so basically this is my GCD calculator. I just call it here in Python, which is basically calculating the GCD as per our algorithm exactly. Okay. All right. And then I'm opening these files for writing. Okay. And looping for 1,000 times, generating data input 1 and data input 2 to be two numbers from 2 to random integers from 2 to 255. Okay. Also, the other one is the same range. Okay. It's just random numbers. And then I'm invoking the function that we just saw up, GCD, to calculate the GCD between the n and one and the n2. And this is my expected GCD. And then I'm going to write the stimuli or the stimuli or the inputs on the input file, and the output, the expected output, the expected GCD on the output file. And then after finishing the loop, I'm going to print a message telling me that the number of tests has been how many test vectors have been generated. Okay. All right. So I can save this, and just to demonstrate it to you, I'm going to run it on the shell, which actually is very much expected. The behavior here is really expected. So to run it, I just need to say Python. You can see that in the top, I have run it here. Now, let me just clear the display here so that it becomes very clean. Okay, so I have I'm calling Python. I'm just calling Python 3 to interpret my Python script here. So generate test files for GCD, right? And you can see that it generated 1,000 test vectors in input patterns GCD and golden result GCD. Less, for example, input patterns GCD. You can see that it is basically decimals that are separated by comma, and in every line, pairs of decimals, that we want to calculate their GCDs, okay? You can see, for example, 71 and 73, most likely the GCD here is 1, okay? So let us test the golden GCD. Yeah, it's 1. Yeah, you can see that most of the time, if you generate random data, the GCD is going to be 1, because the numbers do not, most of the numbers, I mean, and at random, okay, they don't have, I mean, it is highly unlikely that they will have common factors, okay? Especially if you're generating, I mean, if you're looking at a very short time, very short number of iterations, like 5 or 6, okay? So I'm going to stop this video now and continue in a different video to generate the comprehensive test bench for the GCD.